Sweet. Hello, everyone, and welcome to Low Carbon Masonry Construction presented by Larry Rowland from Heidelberg Materials. Right now, everyone is in listen-only mode, so if you have any questions, feel free to type them into the chat, or you can raise your hand and we'll have time at the end for questions. So we appreciate you guys being here. And right now, please introduce Larry Rowland. Take it away, Larry.
Okay, so I just got a message that my internet is unstable, so that's never any good for a presentation. So I'm going to turn off my video and just rely on the screen. Can you guys see my my screen still?
Yes, we can see it.
Excellent. Okay. Well, thanks. It's a small group, so we'll be glad to you guys can do the chat for sure. I'll go through this. This is we're going to talk about masonry construction and why it's sustainable. This is an AIA continuing education course, so we'll offer learning units associated with that. I'm with Heidelberg Materials. Heidelberg Materials is a major distributor and producer of heavy building materials, and we have quite a bit of footprint throughout the world, but certainly in North America. We're heavy into cement, slag, fly ash, aggregates, some concrete, and of course we supply the masonry industry with these materials, primarily cement. We also have, of course, supplementary cementitious materials. We're the largest producer of ground granulated blast furnace slag. We're a very large producer of fly ash as well. The cements that we produce are traditional Portland cements. Then we also have low carbon cements, EcoCem PLC, and then EcoCem Plus, which is a blended cements. And then I'll talk to you a little bit about our Evo Zero cements, which are essentially a net zero cement. So very, very low or no carbon associated with that. We also, of course, supply a lot of aggregates. If you are a mason, you've probably used some of our sands and our aggregates. If you are a producer, you've used our aggregates, no doubt, to produce your products. So what makes a product sustainable, more or less, will depend on what it's made of, how durable it is, how long is the service life will be associated with those materials. Is it easily recyclable? And then is it low carbon? Is it energy efficient in its manufacture and in the materials that it uses? So the neat thing about masonry products, mortar, brick, CMUs, are all made with very abundant, low impact materials. Brick, of course, is clay brick, or is going to come from clay, just like it sounds like. Mortars and CMUs will depend on sand, gravel, and cement. Cement is the most impactful of those products. We'll go into that in quite detail. The other raw materials are ready to go. They essentially just need to be mined and harvested, and then they're essentially ready for use. They have to be resized, of course, and prepared, but you're starting with the material as you want it to be. It's not like iron ore or one of these other products where you have to refine and refine to get to the final product that you want. So it makes these raw materials very low energy and very low carbon intensity, and they are part of an A1 input. We'll talk a little bit about that as well. Masonry products are extremely resilient. They will provide life safety in the cases of fire. Of course, they're exceptional in hurricanes, tornadoes, and in general mayhem. You definitely don't want to be living in a wood structure when there's a wildfire around or if something's burning. You certainly want to have resilient materials when you're exposed to any hazards. So risk is a big issue for our modern society, and masonry products, of course, reduce those risks. They won't burn, and of course, they don't depend on a pressurized water system to ensure fire safeties. And of course, they are not going to be attacked by insects, etc. So very resilient. Resilience is a huge benefit of masonry products. I live in Cape Coral, Florida. This is a image on the upper right here of this is where I live, and the eye of Hurricane Ian went right over my house. Essentially, my home is right here, and this hurricane went right offshore, went over my house. We were the eye actually was slightly north of us, so the eye wall is what went over my house, and all of this heavy duty wind coming in the right-hand quadrant of that took out trees, power lines. But in Florida, where we live, is a concrete masonry town. In other words, the building codes require that we're going to build with concrete masonry or brick, right? We're not going to be building with wood stick frames here in this area. And hurricanes are a big piece of why that is happening. You know, it's very important that we continue to build with these products where resilience is an important factor, because there's a tremendous amount of need for construction. There's going to be essentially a doubling of our building stock in the next 30 years, more than 280 billion square feet by 2040. So there's tremendous need for our materials and for masonry construction. So it's just a really excellent process that we are able to utilize these materials to provide life safety in our homes. Masonry construction is a very good fit for the circular economy. And when you hear that term, think of recyclable materials. Essentially, we get to reuse them again. It's great for conserving raw materials. And of course, it typically requires a lot less energy processing associated with recycled products. And they are part of the life cycle at the end of the building cycle. So once a product is used for the building, and then you have need to either expand or relocate, you can recycle masonry materials. This is a kind of a busy chart, but what it shows us is that the CO2 emissions and the energy inputs associated with CMUs, brick, and other materials are on this chart. You can see concrete is down here in the lower left-hand corner. Concrete block is some of the very lowest energy and, of course, the very lowest carbon intensity associated with these materials. The more processed a material is, such as we talked a little bit about products, such as metals that require a great deal of extraction and then refining to get to the final product. They are up here. They're a lot of energy. This is a logarithmic. So here's a single 1 megajoule. This is 10, and then this is 100 megajoules per kilogram. You can see materials that don't start off in their natural state. You can't go to a mine and pick up plastic. You have to refine oil products and refine or natural gases to get to these products. So they have very high impacts, a very high carbon, very high energy impacts. Brick is right in here. It is higher energy and because of the firing. We'll talk about that in more detail, but it is also quite low in its carbon footprint. It's an extremely sustainable product as well. When we talk about masonry and concrete, they are the world's most used building materials. They account for more than 50% of everything we make on Earth. Man-made materials are typically going to be concrete, masonry type materials. So these are the product of choice because their economy, their strength, their durability, safety that they deliver, and of course their versatility. And they account, because they are such a large portion of what we make, they account to 7 to 8% of our global man-made emissions. Now, I would argue that for more than 50% of everything we make, these are relatively low, but when you have massive emissions associated with all human activity, these numbers are just fairly significant, and we do everything we can to reduce those. And I'll talk about that in addition. When we want to account for our emissions and how we go about them, and what happens is we have a life cycle assessment. And essentially what we do is we look at a building or a project, and we say, okay, what are the different phases? We have the production phase of the materials that go into that building, that structure, or that project, the construction phase of taking those raw materials and putting them in place, the use phase associated with running the building, with the air conditioning, the energy that we pump into these buildings to give us comfort level. This time of year, everybody's thinking about how will we heat our building, right? There's a lot of energy goes into that. And then there's the end of life. So the A1 through A3 is traditionally the production stage. That's considered the cradle to gate. And we'll talk about that in great detail. So if you look at it, the A1 to A3, the modules A1 and A2 are the raw materials, the upstream materials, as we describe them here, the extraction of those raw materials, the initial upstream production of that material. You'll do maybe some primary science reduction, and then moving that material to the factory where it's turned into the final product. The module A3 is that manufacturing phase. That's essentially like, this is a paving plant near my home here in Florida. And you can see this is where the manufacturing happens, right? That's going to be the A3 for a CMU, a concrete masonry unit. You can see here that cement is a big part of the A3 emissions. Cement accounts for only 8 to 10% of the mix, but a full 74% plus or minus of all the CO2 associated with that. So cement is in that in the feed material to make a CMU, to make a mortar, or those kind of materials. Cement-based materials take that cement as a primary raw material input, and that's where most of the CO2 associated with their production is from. Aggregates and the other processes are much smaller impacts associated with these materials. And of course, those are covered in the plant ops in the A3. So I'll unpack that. I'll go through it a few times. Often it helps me quite a bit to go through the repetition. So product category rules are the things that we use to determine how we produce our environmental product declarations. The PCRs help set the rules on how we count and what we count. And of course, there's a product declaration, a product category rule or an environmental product declarations for different products. The product category rules should be specific for the different materials. And of course, there's a PCR for cement that's valid through next year. In that, we describe what is counted in our EPD, our environmental product declaration. Just similar to producing a concrete masonry unit, you can see here in cement production, it starts in the quarry. So we're harvesting raw materials that we need to manufacture the cement. In our case, it's going to be calcium and silica primarily. The main ingredients, the main minerals that we're seeking in our raw materials are going to be calcium, silica, alumina, and iron. Those are the things that we are valuing in our raw materials. Limestone typically is used for the calcium. In the A3, the manufacturing module A3, that's where the real rubber meets the road here in cement manufacturing. That's where our impacts are, because we take those raw materials, we grind them up fine, we put them through a processing to get that aggregate, the limestone, the shale, etc., for our calcium and our silica to the right chemistry. We introduce that into a rotary furnace called a kiln. In those kilns, we heat up the material quite high to about 2,800 degrees. to make clinker. Cement clinker is the product that we manufacture in a cement factory. That clinker is then taken and stored and then grind very fine with a little bit of gypsum, and that's essentially cement. So as we discussed, this is all part of our A3, the manufacturing module for cement manufacturing. This is where the real impacts are. And the clinker that we are manufacturing is essentially a new compound. We've taken the calcium and silica, we've heated it up very fine. They recombined it to new compounds. The calcining is the process that describes driving off the CO2 from the limestone. So calcium wants to occur with, to be coupled with CO2 in its natural state. Calcium will typically not be just all by itself. It will be calcium carbonate. It's oysters, whatever, marble, limestone, they're all different types of calcium carbonate, right? CaCO3 is that chemical compound that is essentially limestone. There are other materials in there as well, but that's the primary source of our calcium, and that's what we're looking for. The calcination is when we heat that material up very high, the CO2 is released. These are called process emissions, sometimes called the chemical fact of life for cement manufacturing. So over 500 kilograms per ton of CO2 is released through this chemical reaction. So that means for every 100 pounds of cement you use in your masonry construction, that cement will have released more than 50 pounds of CO2 associated with the calcination. The rest of our emissions are associated with the pyroprocessing, getting the temperatures in the kiln up to the 2800 or 2900 degrees that we need, and then running the motors, electrical power, those kind of things. So most of the CO2 emissions associated with cement manufacture come from this process emission of calcining the limestone. When we put that all together and we look at the industry average environmental product declaration, or an EPD, we discover that the average CO2 associated with Portland cement's production is 919 GWPs, which means that for every ton of cement, a metric ton of cement, which is 1,000 kilograms, we produce 919 kilograms of CO2. So if you can, it's a straight ratio. So once again, for every 100 pounds of cement that's manufactured, on average, we produce about 92 pounds of CO2. So as a cement producer and as a company that's very much dedicated to decarbonizing the industry, we have adopted very aggressive carbon reduction goals. And we've broken them out. The amount of carbon, according to our cementitious materials, instead of 900, we're trying to get down to 400 kilograms per ton of cementitious materials. This is going to be everything from Portland cements, Portland limestone cements, supplementary cementitious materials. The total production worldwide, we're targeting getting down to 400 kg. And as explained, that is less, much less than even the calcination emissions associated with making Portland cement. So this is a real heavy lift, and we're making it happen. The other thing we're going to do is we're going to capture carbon through CCUS, or carbon capture, utilization, and storage. I'll talk about that in a little bit more detail. But essentially what we're doing is the emissions associated with our cement manufacture are captured and then stored and/or captured and used to make another product. So this is a really very complicated and heavy-duty technology. It's very new for our industry, and we're embracing it in a big way because we have committed to capturing 10 million tons cumulatively by the end of this decade. So these things are all the way that we are going to reduce the CO2 associated with our cement manufacture is we're going to reduce the clinker factor in our cements. We're also going to, of course, produce and sell supplementary cementitious materials. So clinker, that material that we manufacture in the cement factory, in ordinary Portland cement is about 94% of the content of the cement. In Portland limestone cements, we've increased the limestone portion of the cement, and so we've reduced our clinker factor down about 10%. When we're utilizing EcoCem Plus or blended cements, we are able to reduce that clinker factor dramatically. We're able to get the clinker factor for the type 1S40, which is a Portland slag cement that we manufacture in Evansville, Pennsylvania, is only has a clinker factor of 56%. So we've put in 40% slag, with the clinker is 56%, and then we've got a little bit of limestone and gypsum in there to round out those numbers. So blended cements are very much going to be in the future, not only for Heidelberg Materials, but the entire industry will be going towards those. I already said that a standard Portland cement has a GWP, a global warming potential of 919. And you can see here for the type 1-2 that they manufacture at this Evansville plant, it's 841. So that's already much lower than the industry average. It's a very efficient plant. And then you can see here for the type 1S40, that's only 531. So we're getting down near our targets. This cement helps us every day. Every ton of cement that we sell, that is this type 1S40, which is a terrific cement that people really love because it is a pre-blended SCM in with the cement. We're able to reduce our GWP with that cement dramatically. So it's a really neat product. And once again, our customers are very much appreciative. Of course, cement, as we said, is key for low carbon CMUs for concrete masonry units, and of course also for mortars, because cement is such an important part in the production of mortars. So the way that we're going to reduce our carbon footprint in the cement is we're going to reduce the amount of clinker in our cements. We're going to be very energy efficient. We're going to utilize alternative fuels, etc. Ultimately, we have to use carbon capture, utilization, and storage because that's the only way to offset or essentially capture the CO2 associated with those process emissions, that calcination emissions. And then the other thing we're going to do, like we said, is going to reduce the clinker by producing blended cements, and also by utilizing supplementary cementitious materials. And of course, architects, designers, and folks that are working with masonry assemblies can also help tremendously by using the right block for the right block and brick applications, and then also, of course, using the right size design. No reason to put in a lot of extra materials that are unnecessary for the project. I've mentioned supplementary cementitious materials in my presentation already a few times. Most of you may be familiar with those, but in case you're not, SCMs are typically going to be, in this country, they're going to be slag cements and fly ash. Those are the two primaries, but there are lots of different materials that we can put into a concrete system to replace the Portland cement or replace the Portland limestone cement binders. And of course, these materials, a big advantage of these materials is they typically come from waste sources. They are waste products from other industries, and they have very low global warming potential. So very low embodied carbon in these materials. In Canada, they take a very unified approach to how they specify SCMs. They're all part of a unified specification for cementitious materials. In the United States, we have specific ASTM and ASHTO specifications for these products. Coal ash, which is fly ash, I've mentioned fly ash quite a bit. That is a coal combustion product. And the specification for the production and use of this material is ASTM C618. And it, of course, controls the reactivity, the chemistry. So the nice thing about, you always want to make sure that your raw materials meet a designated specification so that you get the quality and the reproducibility that you're looking for. It's very important. All the materials that we manufacture and that the industry supplies as a whole will be according to an ASTM specification such as this. In the United States, we produce a lot of fly ash. You can see this is the total coal ash production over the last 15 or almost 20 years. And you can see there's a tremendous amount of coal ash produced. We're talking in the 135 million tons annually back in 2007. That has dropped now. We're in the high 70s, say 76, 78 million tons of this material. And you can see that we do utilize about 15 to 18 million tons in concrete. The total use for all different applications is about half of the production, but there's always a lot of excess. There's a lot more coal combustion products produced than are typically used. And that's where this technology comes in. So the STAR technology, which is our technology, Heidelberg Materials, purchased a company named SEFA, Southeast Fly Ash Company. SEFA produced and pioneered this beneficiation process. Essentially, all that excess fly ash would go to a landfill, typically for decades and decades since the Clean Air Act back in the early 1970s. Energy companies, people burning coal to produce electricity, had excess fly ash, excess coal combustion products, and they would put it in a landfill. And so it has been for the last 50 plus years, the number one material landfill in North America. We are able to go out and harvest that material from the landfill, beneficiate it because it's not a cementitious material by itself. It's reactive, but it was essentially exposed to water and put in the landfill. We're able to extract that material. We're going to size it. We're going to drive off the moisture, drive off the carbon that's there, any waste carbon, and make that a reactive, very beneficial application. The people who utilize this fly ash at a tune of over 1 million tons a year annually report great results because it's extremely consistent. It actually will be more consistent than the fly ash that you would get directly from the power plant these days. So it's a very good product, and of course it's very sustainable technology because you're taking a waste product that's sitting out in a landfill and you're putting it to good use. The other material we talked about for the number ones and number two supplementary cementitious materials used in North America and pretty much around the globe is slag cement is the other one. So slag cement is actually ground granulated blast furnace slag is the long name for that. It's because it describes what happens in the primary iron manufacturing. We talked a little bit about how other materials, you have to take something that doesn't look like its finished product. At the beginning, you take iron ore and you put in some limestone with that, a coking agent, and essentially you heat them up very, very hot. The primary molten iron from that is siphoned off, and then on the top, the slag actually floats to the top of this molten iron, and that's siphoned off, and then that's quenched. And it has to be quenched rapidly. And when you do that, you produce these and you put in what we call a granulator. That equipment, that quenching process ensures that you come up with this material. This is granulated blast furnace slag. We take that blast furnace slag and we grind it very fine and it becomes a cementitious material. So the process is to take those granules that look essentially like a coarse sand, run them through a cement mill or a grinding mill, a finish mill, we typically call those, to make something that is as fine or a little bit finer than Portland cement. It's very important that these materials are to meet the specifications, the ASTM-C 989, which is for slag cements used as a supplementary cementitious material, and they can also be used as a blended cement. I mentioned earlier our type 1S40 cement that meets this ASTM-C 595 spec. What the granulator that I mentioned is very important. So you can't take the slag from the blast furnace and let it just air cool, because it becomes inert. It's essentially a rock at that point. It's not nearly as valuable because it's essentially inert. It could be used for fill and those kind of things. But if you install a granulator and you freeze the chemistry through the quenching process, it becomes very much like Portland cement. So the reactive materials that are within it, you can see it has essentially the same mineral ingredients, but at a different ratio. So it doesn't have as much calcium, but it has the silicates. And of course, when you grind this very, very fine, it is a cementitious material. Once slag cement has been ground, it is not inert. It will react by itself with water. It won't gain very much strength. However, in a concrete system with Portland cement or Portland limestone cements, it is very beneficial. And most ultra high strength or very high strength mixes will utilize slag cements in them because they're so beneficial for the mix. Other applications, other specifications, or other supplementary cementitious materials that we're investigating are materials from waste streams, such as biochar, which is a specialized type of an ash that's produced traditionally from agricultural applications. And then, of course, we can take waste glass, that recycled glass that we all put in our recycle container, can be ground up very fine, and in special applications, and when it's treated properly, can turn into a pozzolan. It can be a supplementary cementitious materials. These materials and fly ash don't have the same replacement value as slag. One of the reasons slag's so good is it has a very high replacement level. These tend to be fairly low just because of their nature, what they are. Other materials that we're investigating include calcined clays. You can utilize calcined clay just as an SCM, or you can actually produce what we call limestone calcined clay cements, LC3 cements for short. Metakaolin is a product that you may be familiar with. It is essentially a high alumina calcined clay. So they have a good track record, and we are working to introduce these products globally and here in North America. And as the industry learns to use them, they can be very effective. There are also natural pozzolans here, predominantly from volcanic deposits. Now, I mentioned carbon capture and storage. This is big equipment, and it's a big, complicated factory, essentially. In most cases, the equipment and the facility that you need to capture the CO2 associated with a process such as cement, the industry cement, or even other industries, will be as big as the cement plant practically. So you end up having to build a second plant just to handle the carbon, just to capture that CO2. You can see this is Sven. He's about a 7-foot tall Norwegian, and he's standing right next to the trailer here of this big stack. You can see this is part of our carbon capture and storage process. This is in Brevik, Norway. It will be the world's first industrial scale carbon capture and storage plant. We will be capturing 400,000 tons of CO2 associated with this. It is now essentially in place this year, or it's mechanically complete, and we're firing it up and getting that process going. We'll really be in earnest. It'll be in full operation in 2025. We'll be dialing this in. This is brand new and very complex technology, so we anticipate that it'll take a little while for this to actually be working. But when we get this in place, and as we're capturing the carbon associated with our cement manufacture, this will enable us to produce an EVO Zero cement, which will be made available first in the European market essentially a net zero cement that is available. The Brevik project is just one of many that we have going around the United States, or the whole world, I should say. In the United States, we plan on doing the plant in Mitchell, Indiana. We are in early stages now, doing test wells and evaluating our ability to capture and store the CO2 associated with that plant. We are working very hard to get the plant up in Edmonton fitted. The plan is for Edmonton to be the world's first full-scale CCS project. So in other words, all the CO2 associated with the million tons of CO2 that are produced in this million-plus ton cement plant will be captured and stored permanently. And then, of course, Mitchell is twice as big, and we plan to capture all the CO2 there as well. So we have quite a few technologies, quite a few different projects out there that are in place. And once again, we're trying to support this goal of capturing 10 million tons cumulatively by the end of the decade. So we mentioned it here just as an illustration of how important this is. This is essentially, remember we said 74% of the CO2 associated with the production of concrete masonry units will come from the cement, and then other raw materials, and then the plant operations are a pretty small piece of that, right? Well, when we produce our Evo Zero cements, this entire thing changes, right? So the cement is no longer going to be a source of CO2 because the CO2 associated with that cement will be captured and stored. So your entire carbon footprint for manufacturing your CMUs, for manufacturing mortars, etc., will dramatically change and go way, way down. So let's go back and bring this back home to masonry. So CMUs have the CMHA has helped produce a CMU industry average environmental product declaration. The information I'm going to go through here will be taken from that for the next few slides. Essentially, what we do is we look at a cubic meter of concrete that's formed into concrete products, and we add up all the impacts, and we determine how much emissions there is, how much waste, etc. The whole shoot match. It is an environmental product declaration, which gives the impacts for the whole product. So as we said, cement is only, you can see about 8 to 13% in this case for the higher different products, but it is the biggest piece like we talked about here. The EPD from the CMHA has identified different classes of concrete masonry units. There are 3 normal weight blocks, essentially, 2 medium weight materials, and then 2 lightweight CMUs associated with that. And of course, if we look at the global warming potentials, which stands for the amount of CO2 or equivalent, or the amount of CO2 associated with a cubic meter of this mix, you can see here for normal weight blocks is the lowest. In this case, the lowest strength class. You have GWP of only 208, and then the top GWP is up here at 280, or excuse me, 395 is the highest. That's the lightweight block. So you can see the different materials, and that's the range of the GWP associated with these. Quite low compared to cement, of course. They are in line with some concretes. They tend to be lower than typical concretes, of course. However, there's this very important footnote associated with a declaration. The footnote will tell you that the global warming potentials for these products include the calcination carbon emissions, which, remember, that calcination emission comes from the cement plant. When I drive off the CO2 associated with the limestone, that's a calcination emission. It includes the calcination emissions from me, but it also includes natural carbon sequestration. Essentially, and I'll go through it here, but essentially what happens is you have the plus emission associated with the calcination, but you have a minus associated with that sequestration through carbonation. The reason that works and the reason that it's an important thing for concrete masonry units is that the natural carbonating process is very effective and very widespread because of the open matrix associated with the CMU. So instead of being a tightly bound, a tightly packed matrix that you want to fill every single void because your goal with a typical concretes are to get a very high strengths. CMUs don't have to have that strength. You want light. You want to be able to handle them manually. So you tend to avoid utilizing all that sand. The void system lightens the block, but it also provides this very interconnected void matrix so that essentially the atmosphere can reach all the different coatings. Each one of this is a polished section. So each one of these little bits of rock and sand, here's probably a rock you can see, this is 1 millimeter. And then also all these little bits of sand are all coated with cement paste. Well, as you can see, the outside is where that paste resides. And as the atmosphere, as the CO2 enters the system, it recombines with the available calcium. Calcium doesn't like to be left alone. It wants to combine with CO2. And so we've basically recarbonated the calcium associated with that calcination process. Tests show that 21% of all the calcination CO2 associated with a cement manufacturer that happens in the production of all the materials that go into your block, within 28 days, 21% of that CO2 is reabsorbed. So it reduces your GWP by 18 to 22 kg per cubic meter. Within 2 years, 49% of all that calcination emissions are sequestered and picked up. And of course, you have a much higher reduction in your GWP because you've reabsorbed that CO2. That natural carbonation is a huge carbon sink in the system. Thank you for the CMHA for these images and this information. Natural carbonation, here's another way to look at it. This is in a concrete system. Once again, if you recall, in the masonry unit, there's a tremendous amount of voids. In a standard concrete, essentially you're trying to eliminate your voids. You want to get it down to where there's essentially no voids. And the CO2, you can actually put a dye on the concrete. And as the concrete carbonates, as the CO2 is absorbed, the dye changes color. So you can see just on the surface of the concrete of a traditional concrete is where that carbonation depth happens. That's where the CO2 reacts with the free calcium and becomes CaCO3 in that process. Concrete gains weight. Masonry blocks gain weight as they absorb this CO2, believe it or not. The process you can see here is you've got CO2 plus some water, which is it can be water vapor, produce calcium hydroxide, which combines, and essentially you're forming new limestone, right? So it is a natural phenomenon that's going to happen whether you try to make it happen or not. This is part of what happens with all concrete, and in block, it's a really big factor for us because of the exposed surface area associated with the block, and of course any treatments and the different applications. Because the geometry of the block is such that it leaves a lot of voided spaces and openings. You get a tremendous amount of carbonation. You get this natural sequestration of the CO2. So these are sections of block. In 4 weeks, you can see that We're getting into this a little bit into the surface as that block is exposed to the atmosphere for a couple more weeks. Where we're at 13 weeks. You can see it's penetrated even further, and then this is in a half a year. It's penetrated almost completely through that concrete matrix of that CMU. So the natural carbonation reverses the calcination process. So you've taken calcium with CO2 and recombine that to make new CaCO3. Essentially, you're making limestone in place here. And of course, like we talked about, the geometry in the open matrix is what really makes concrete or CMUs such a wonderful sink. They're really the real benefit associated with natural carbonation is seen most predominantly in CMUs. I haven't talked a lot about brick, but of course, brick is also super resilient. It provides all the fire safety, all those different benefits associated with any masonry or concrete system. The BIA has produced their own environmental product declaration. The industry average EPD is for all these different types of bricks. So they've gone through and they explain that clay brick is made with these materials. These are the different types of bricks that were studied and included in their study. So it's a very broad range. So if you utilize brick, you can pretty much count on this EPD covering that type of brick. And of course, cement has a high role in the production of mortar, but not in clay bricks. You don't have the cement as a factor here. So the A1 associated with brick is very low because essentially your A1 is your material extraction and the mining of that clay and just the processing of the clay and getting it ready to fire and make the brick. So the A1 is very low. The A3 production, which is the emissions for the firing, the drying of that clay, etc., and turning it into a solid material, is where the impacts are. The GWP for a cubic meter of bricks, 750 or so bricks, whatever the right number is, depending on the geometry, is 503. So it's relatively high compared to CMUs, but you have a lot of energy here, a lot that you have to account for, and that's why that's that way. They are, like we talked about, the EPD gives us these ingredients. It's 95% essentially of shale. You can utilize, I said shale, but it's also, of course, clay and shale. You can, of course, utilize supplementary cementitious materials and other recycled content that can go into that. And by mass, they tend to be fairly small industry-wide. But of course, the benefits are still there. It's still very abundant materials. It, of course, has a lot of thermal mass for insulation. It can utilize different kind of fuels. You can utilize alternative fuels in your firing and in your drying processes. And of course, it's super durable, super resilient. And of course, the brick is a beautiful product, so you can have a natural finish. There's no need to paint brick in place. So the key takeaways for this presentation are that the materials associated with masonry construction are very sustainable. They're resilient, they provide great life safety, and they are well-documented impacts, environmental impacts associated with this are documented in the environmental product declaration for these different materials. Cement's role is a critical role as a binder for mortars and for concrete masonry units. Heidelberg Materials is the leader in our industry. We're taking action to decarbonize the industry. Supplementary cementitious materials are a great way to reduce the carbon associated with your different products that you manufacture. And of course, in the future, we're going to utilize carbon capture and storage to account for those calcination emissions. And we will be able to produce a net zero cements that we can make available to our customers. The cement that is manufactured is exactly the same. The only thing we're doing is capturing that carbon associated with the production. The cement is the same. So if you are an AIA member and you'd like to get continuing education credits for this, you can scan this QR code. It'll bring up this sign-in sheet. The sign-in sheet will automatically be once you fill it in, we'll follow up with you and we'll send you. We will register your name with the AIA, and we can also send you a certificate if you'd like for the presentation. So. I'm glad to take any questions. Once again, here's the QR code for the AIA. It looks my internet has gone unstable again. So why don't we go right to the any chats? It looks like there's in here.
I put my
That's
I
just
just
you
put my
putting your
email in
email in
there.
there. Cool.
I put my email in there. So if you guys do have any questions that pop up after the webinar ends, feel free to email me and I'll work with Larry to get those answered for you, as well as the QR code. Larry, do you want me to just put your email in there too, just in case?
Sure. Matter of fact, I'll type it in here. I know how it goes.
Perfect. As of right now, I'm not seeing any questions, but we can definitely hold on for a minute.
Well, I appreciate everybody coming. It's a small, intimate group, but hopefully the information was helpful. And we'll track a course who registered for the course and is here. If you'd like us to follow up, please just drop us a message, either Justin or myself, and we'd be happy to reconnect with you and give you some data if it's something that you're looking for.
Yeah, awesome. So again, if you have any questions, feel free to just stick around, but as of right now, there are none. And if you want to contact Larry directly about any questions, feel free to do that. If you guys have any questions about future webinars or anything like that, feel free to email me. Mine's at the top there. And thank you all for being here today.
Yeah, I appreciate everybody's
Larry.
attendance, and wish everybody a very happy holiday.
Awesome. Thank you, Larry.
All right, cheers.
Cheers.